Welcome to ALD Stories, a series chronicling the personal journeys of the people behind atomic layer deposition, untold stories of the technology, and deep dives into the history, development, and future of ALD. I'm your host, Tyler Myers, bringing you this podcast from Benek, the home of ALD. There are few industries as prolific as the semiconductor industry, and few that offer incredible careers full of innovation and fast-paced change at every corner. Our guest in episode 24 is one who has fallen for semicon and found great successes during his nearly 3 decades in the industry. ALD Stories is pleased to welcome Dr. Fred Roozeboom to the show. Fred, currently a professor at the University of Twente, where he originally received his PhD, started his semiconductor career at Philips Semiconductor in 1983. The majority of his time was spent working on the 3D integration of passive components, which resulted in him being named an NXP Research Fellow in 2007. He later joined TNO Holste Centre in 2009, where he kickstarted his ALD career, specifically as a technical advisor to those working on spatial ALD. After a successful career with technology transfers resulting in innovations like Medtronic's minimally invasive pacemaker, Fred was recently awarded the Gordon E. Moore Medal for Outstanding Achievement in Solid-State Science and Technology from the ElectroChemical Society. In our episode, Fred and I talk about the semiconductor industry in the 80s, his original work in rapid thermal processing at Phillips, and the importance of passive integration. We also discussed the Medtronic pacemaker, his world record during the great reintroduction of spatial ALD in 2008, and the applications he's most excited to see come to life with atomic layer deposition. Big ups and thanks to Fred for his stories, so without further ado, please grab your tea or coffee and enjoy episode 24 with Fred Roozeboom. We can go ahead and get started. So, good morning again, Fred. Welcome to the ALD Stories podcast. I'm really excited to have you here. We have, I think, a lot of topics that we can talk about today. We certainly touched on quite a few when we chatted last. So again, welcome. It's really nice to have you. And I'm looking forward to our chat today.
It's a pleasure.
So it's hard to say, I think, where to begin with this conversation. I mean, we started basically your entire history in semiconductor processing and ALD and material science from your PhD all the way to your appointment now at the University of Twente, and it's hard to say which one we should land on first. But I think I would like to maybe start just after your PhD. So after you finished your PhD at University of Twente, you went to Phillips, right?
Yeah, in between it was 3 years America, ExxonMobil, catalysis. But upon my return, I decided to look for another job, which ended up at Philips Research. Yes, correct.
Okay, great. So it's a really interesting time in the 80s for semiconductors. So before we get into the real meat of it, just what was the motivation after you finished with Exxon wanting to then work in Philips?
I know that in fact, I wanted to in America, it was at one of the corporate research labs that I was working for in catalysis. Coming back, it was in a very applied technology group, small group, a dozen of people at the refinery. And that was one step they went to make me a manager or so, but I wasn't ready for that. And I wanted to stay in research at a big corporate institute. So either Shell or Philips, and it was Philips that ended up as my next employer.
I want to talk a little bit about what the kind of atmosphere in the semiconductor industry was like there. I'm a little bit familiar with the time from the U.S. I know the 80s were about where Japan started to come on the rise. The U.S. industry was not having a great time. But what was the atmosphere like at Philips? I know they were, also doing really well. They were one of the top, manufacturers at the time. So what was the atmosphere like around in the industry then?
In fact, I could say, especially when I started there in 1983, it was a wild cradle of any new leads, scientific or technological. We, that is the research staff, got maximum freedom. If I look at it now in hindsight, I can say, and I already sort of perceived that in the very first years, maybe it was a little bit too free life there, not only for me, but for all of us. So on one hand, that is great for real novel inventions and that sort of thing. But the step from good scientific or technology leads towards redevelopment, marketing was a bit too sluggish. So the Philips research labs were fantastic. The trajectory to commercialization was a bit hindered, I would say, hindered by non-optimum channels and that sort of thing. But speaking for myself, I had, and most of the people but at Philips Research in those days had great times. And there were a lot of inventions and new things that made it to the market anyway.
I'm sure that once you made the move to silicon, it was like, endless possibilities at the time. There's, I think, maybe a little bit of a structured roadmap now, but I mean, yeah, the 80s seems a little bit like it would have been the Wild West.
Yeah, and on top of that, you just mentioned that Japan was coming on and strongly, but Europe was a big player in those days also. So in France we had ST, and we had in those days Siemens, and now what is Infineon, and so in Germany, and we as Philips had great European projects, very massive projects, especially the Mega project. So that was for the megabit chips. Philips did the static RAM, and Siemens did the DRAM. Those were really front runner projects in those days. Yeah.
Did you feel like there was pressure on Europe in the same way that there was in the US, like Intel and those companies?
Well, in fact, I could if I think about it, I still think that those worlds were not that globally integrated by then, because all those companies, also the French, the Germans, and Philips, had their own semiconductor worlds and market shares and so forth. There was less. Well, the only thing I can say, by the way, is that when that mega project came on, Philips Research started building all sorts of porto cabins extra and hired experienced people from Intel and others at extreme salaries, by the way, to get that knowledge expedited in the mega project. Yeah, great days. Money was no problem at all.
So that first then period of time that you were working on Philips, what was the main projects that you were partaking in?
I was mainly involved in rapid thermal processing. It was called later on, and it started as rapid thermal annealing. So that is just to activate the implant areas for source and drains with a rapid heat pulse in order to get the dopants, phosphorus, arsenic, and boron, sort of incorporated into those source and drain areas, as well as rapid thermal oxidation, also gate oxide formation at a reasonably small process time scale was getting more and more attention. It was in the times that also the semicon production equipment started going from multi-wafer, so 100 or 150 wafers in a horizontal and later on in a vertical oven for diffusion, oxidation, whatever you had, towards single wafer processing. That was in the 1993. I think the tipping point was something in 1993 that more and more single wafer processing was going on. Let's say the pioneer in those days were Texas Instruments, Dartmouth Leahy, who really had a full in a special clean room, a full single wafer process equipment flow chart, so to say, to fully process wafers. I believe then in those days with 2 or maybe 3 metal layers, with all the steps in between, all single wafer. And of course then thermal treatment, thermal annealing, rapid thermal annealing and rapid thermal oxidation or nitridation or whatever you had, was in those days also sort of phasing phased into the single wafer process flows, which now are a normal thing to do.
Mm-hmm. Well, what was the kind of drive or tipping point for why they were making the transition to single wafer?
Well, one of the driving thing was, of course, that let's start with diffusion or dopant activation. Why would RTP rapid thermal take over? Because the thermal so-called budget, so that's in fact temperature times process time, was getting too high in those bulky high thermal capacitance ovens, in such a way that any undesired side reactions that always take place would take over, rather than the intended oxidation or activation that you wanted. And in such large furnaces, the thermal mass is that big that you could not really suppress enough those undesired reactions. Example, if you would like to activate the phosphorus or the arsenic in the N-type parts in the source drain process, then diffusion of those implanted atoms would take over, rather than the incorporation of the atoms into the silicon crystal lattice. Yeah, they would run away and they would exceed the dimensions, the critical dimensions of the source and the drain areas. So temperature was getting very critical, and meaning that especially the temperature budget should be limited. And in a single wafer, you only have a single wafer as let's say the bulk thermal mass component.
I imagine that the integration of that equipment maybe was a difficult thing to do at the time. Was it a couple years to kind of make the transition, or to get the single wafer equipment in, or did it take quite a big roadmap, long time span to make that happen?
Everything in this area of semiconductor manufacturing still today is all about cost of ownership. It's cost. And that is why, of course, a lot of manufacturers, Philips as well as the others, also the big ones today, if they can stay in whatever equipment, in whatever environment that does the job to let's say to meet all those constraints and the critical dimensions in particular, and let's say the sheet resistance and whatever parameters you have, as long as they can do it with old equipment, they will stay there. It is only when the knife is pushing too much on the throat that they will let's say step over. With many words, I'm saying something that period of transition has taken something like 5 to 7 years, being the depreciation time of equipment in general. Only if they must, they would and they will change.
That sounds very familiar to many conversations I've been having recently about the integration of ALD, and that when it first came out, everybody's like, okay, we'll just repurpose the CVD equipment to do ALD. Why get a new tool?
Yeah. Well, of course, another thing is, CVD is so much decades older and longer and well matured. And CVD still does a very good job also in upscaling, upscaling in the sense that the wafer size is larger and that sort of thing. Throughput is also one of the considerations. That often is a sort of obstacle for ALD to really break through in all sorts of processes and material depositions or processes. It is, of course, it is about the cost, and it is about the future or the present specifications in such a technology option. So ALD is, of course, it is very well established now for just a few, let's say a few real high volume manufacturing process steps. The gate oxide, again, that was necessary because especially in those furnaces, you could not keep the, let's say, temperature budget that small enough. So it would, the oxides or the other dielectrics would grow less controlled than you would like to. And only then ALD came up with the sacrifice of process time in the beginning.
Yeah, great. So, okay, so you were working on RTP for a little bit. Now I can't quite remember. Did you have a time in between where you left Phillips and came back when it was now NXP, or were you there through the entire transition?
I was there through the entire transition from Philips to NXP because that started. I mean, the disentanglement of Philips and what now is NXP started in 2006, and the full transition was in fact complete somewhere in 2008. I was still there, but on another payroll, still even in the same room with my colleagues. The physical sort of separation also of our workplaces had not even started. NXP decided to do their production. In the beginning they said Fab Light, but it turned out more to be fabless. They still have a couple, it's just less than a handful of plants where they do their production now. So in Holland, there is still a big plant in Nijmegen. It's sort of in the mid east of the country, near the German border. And of course, most of their products are now being made in Taiwan, TSMC, or in Singapore, SMC, what is it? SMC, Singapore Manufacturing Baba. But that's about it. So, in fact, they decided gradually from 2008 to 2009 or 10 to move into fabless or production. Yeah.
Mm-hmm. That initial divestment from Philips, was that kind of on the horizon? Did people know that was going to happen, or did it kind of come out of the blue?
It did not really come out of the blue as a phase before you could, because it's all about cost. Mm-hmm. As a phase before, there was in the early 2000s that Philips Research Management decided to relocate all of their advanced CMOS technology from their own clean rooms to IMEC in Leuven, Belgium. So two major groups were relocated there and were sort of transformed in a permanent partnership, which exists still today. Because there is still also a partnership locally there with Lam Research, with Applied, with ASML. No longer with NXP. They do NXP themselves do now only their design and their prototype testing in what's still NXP labs in Holland. But all the things in between or afterwards, mass manufacturing and so, is done in the foundries that I just mentioned.
See, okay, interesting. So when you were then working on this passive integration work at NXP, was this then mostly design work, and did you have then some collaboration with the fabs and foundries, or?
Yeah, but I'm just a simple thin film technologist, so it's deposition, etch, and that sort of thing. I did some designs, but there I was much more dependent on others in the group or in the groups. And early on in research, we found within Philips Semiconductor, so in the product division, we found interests at two other plants, one in Nijmegen, one in Caen, France. But Caen was the real setting for us to develop these system in package multi-chip packaged products for in the beginning for RF communication, wireless communication. And that was fun because we concentrated there on the passive part. So imagine it was basically two chips, one ASIC that was sort of coming from other sources, and we did the passive chip with especially the trench 3D capacitors made into that chip and fully integrated in a silicon design, also with resistors and inductors.
So I understand, like, okay, these kind of passive analog components, they scale a little bit slower than some of the active ones have in the past. Is that correct?
It's but that's a very good remark. And if you all go back to 1965, when Gordon Moore, just the late Gordon Moore, iconic person, published, let's say just a few pages, what became the Moore's Law or so. In the there's two very interesting things if you would look it up. In the abstract, he really mentioned the word economics. So the scaling was all about money. Yeah. And in the very end, he makes a few remarks on scaling passives. Because you're making a very good remark here. Passives are not that easy to scale in a 2D sort of configuration. And in those days, which is now 60 years ago almost, when he published this paper, in those days, people were hardly thinking about 3D sort of processing. They only sort of occupied the field of the surface, the very surface of your silicon chip, and all the structures there were just 1 or 2 micrometer total layer stack or so. Nothing 3D, it was all 2D. And having that in mind, he Gordon Moore, ended with a remark, scalability of the LCR components is not that easy. No, that's right. An inductor is hardly scalable, and a capacitor, and that became our work at Philips, is scalable if you make it in an intentional 3D sort of trench structure. And nowadays, everything, also in memory and in logic, everything is now 3D. But that was not sort of envisioned in the mid-60s in those days.
Okay, and that's fascinating.
Yeah, and still is physical. It's physical, so physics limits that sort of scalability on 2D substrate surfaces.
Okay, that's great, because my next question was going to be whether, at what point basically did scientists realize, okay, we need to figure out some way to integrate these in a packaged way instead of on the same die, because the node technologies aren't matching up. But if it was already known in the 60s, and okay, so when you were working on it, then it was nothing new.
No, but there is a lot of things to say. One remark that, and I'll make a note that I don't forget the others or so, but the thought of using 3-dimensional silicon, those very first thoughts were in the mid-50s. There's two persons that I would like to mention. that is Shockley, the co-inventor of the transistor as such. That was I believe it was 1957 that he filed for a patent on which we now call through silicon vias. So those are sort of etched channels very deep into a piece of silicon, a substrate of silicon, and so on. He didn't. The word TSV did not exist, but the patent is there. So speaking about visionary technologists or scientists at TSVs, so that was there. A year later, 1958, many people will know Richard Feynman, very, let's say, very talented and unbelievable guy who had late 58 this talk, and you can find it on the web, which now is sort of encompassed by the word there, by the sentence, there's plenty of room at the bottom. Yes. So meaning dig deeper into 3D, and you will have a lot of extra possibilities which enable far more high densities of functionality in a silicon chip. Because in fact, silicon substrate, typically it's 700 something micrometer thick. Only a few micrometers in the very, very first days were used, and nothing of the rest, almost a millimeter. And now through silicon vias, all that sort of things are now just business as usual. It started, of course, in fact, with the breakthrough late 70s of deep reactive ion etching. People could do something with wet etching in the earlier days, but wet etching in general is isotropic. You get all sorts of undercut under your masks, and so you cannot densify or scale down the dimensions further. Anyway, so TSVs is one of the very, let's say, major developments that now enable also chip-on-chip stacking, and you know that this sort of thing, your USB stick, is in fact consists of a stack of homogeneously integrated memory chips. They're no longer 1 millimeter, but they are thinned down and then stacked upon each other and connected with each other through those TSVs.
Okay, that's great. Yeah. I did not know that.
Okay, yeah, so something like, I think it's now even 12 thinned down chips, just equal, identical chips on top of each other and connected through these TSV technologies. Anyway, this 3D is now the name of the game today, especially with ALD.
Yes, yes, absolutely. So when you were working on passive integration, are there some products or some place in the commercial space now that that work is being used, something you're really, really proud of that you could see it in today?
We managed to transfer the knowledge also to Medtronic, which of course is let's say a medical device company in the US, and it's the world leader of pacemakers. And imagine, that gave me much pleasure to sit down. I went there 3 times, including their plant in Arizona, where of course production ends up. But first, of course, this was preceded by a period that the plant in France and myself and my team members, I had a team of 12, 13 people there at research, but we sat down regularly to make the roadmaps for these, trench capacitors. And the roadmaps, we already could foresee that if we would and that's an old story, of course, now. But if we would replace the silicon oxide or oxynitride dielectric in the transistors by higher K, if we would also densify the trench arrays also a bit or make them deeper, we could really walk down a roadmap from capacitance. In those days, it was typically just 30 nanofarads per square millimeter, 2D millimeter, top view, from 30 nanofarads, and now it is around 1 microfarad. So those densities have become 30 to 35 times denser, and that enabled Medtronic to let's say to manufacture ever smaller or ever denser pacemaker designs, and of course other components in those pacemakers have also been miniaturized, but important were those capacitors. In the days that we started, it was like, well, sort of silver dollar diameter, the pacemaker in a titanium casing, and then patients who need those pacemakers, they had to go to the hospital where they were sort of open up your breast and your ribs to implant the pacemaker. But nowadays it is that small, and you can find it on Medtronic's website. It is now that small that it is implantable through one of your main veins with a stent. And then the pacemaker itself, it has now got a sort of, call it fish hooks, all miniaturized, and they hook it up to one of yours. I think it's called the pectoral muscle of your heart. And so it is, it's not completely non-invasive, but it's, let's say minimum invasive rather than, going to, undergoing that sort of major surgery.
That's amazing. I'm sure very satisfying for you to know that that's where it is now.
Yeah. But again, credit to them.
Mm-hmm.
Yeah. And I can take a little bit more credit for the trench capacitors in RF, and so because that's what we build up. And Phillips tried to kill it internally every now and then when the money was going down. I could save it with European projects and then national projects, until it really was taken over in France. Sometimes ideas, especially with Philips research in those days, ideas came too early. You must have a killer application market and simply be lucky. I have been lucky.
Mm-hmm. I'm sure that there is sometimes a low tolerance for more fundamental research, what feels academic.
Yeah. Like also these days, and all sorts of companies are sort of focusing or cutting, but sometimes it's also good. For example, ALD had the big letters behind your face. ALD is still flourishing very, very, very much. Yeah, like lithography and ALD for good reasons, because those are the two enablers in continuous scale down.
Well, this is a good segue then, because the title of the podcast is ALD Stories, and we've touched on ALD slightly, but of course I think we'd be remiss to not talk about your time in ALD as well. So now this is post Phillips. You moved to TNO first, I believe, to start doing some work on ALD. So now, what motivated the switch then? You're kind of really changing, not totally out of the same area, but it's a bit of a pivot, I imagine.
Yeah. But let's first take then in the historic way my leaving NXP. I already explained NXP was going to leave technology, in fact, almost completely, because they were fabless or fab light. And in those days, 2007, as a matter of fact, I already started as part-time professor at TU Eindhoven for the ALD part, purely for the ALD part. In 1-2 years earlier, when I was still at Phillips, 2006, there was this conference, one-day conference, IOP, Institute of Physics in the UK, where I was invited and talked about, the very first trench capacitor successes. And then a guy, John Burgoyne from Oxford Instruments, after the conference, I was already walking back to Waterloo Station. He asked me, could we do something together? We, that is Oxford Instruments and Philips, could we do something together? We knew each other. We, Oxford Instruments and I knew each other for the plasma CVD and whatever we already had there. But John explained me they at Oxford Instruments, they also had an interest in ALD and plasma ALD. So, and were seeking some cooperation. So I had them over at Philips Research, but from their questions, it was clear that they had to come from scratch. Yet, although they were very good already in plasma, CVD and etching, in that discussion at Philips Research, I said, "We are not the place to develop things for you. You should join TU Eindhoven." I was already sort of contacted by them also to join as a professor, and that turned out to be until today, as we speak, as a very good initiative, because Oxford Instruments now has got permanent presence of one or two of their payroll people, Harm Knoops, who you interviewed lately. Yeah, now that's one thing. Then I became part-time professor there, still at Philips and NXP. And now your question, NXP was leaving technology. What the hell should I do there?
Sure.
Yeah? And I wanted to stay. I was asked by the CTO then, Henk van Houten, Fred, do you want to stay at Philips or NXP and so forth? I said, no, I love Semicon too much. And same question with NXP, going fabless. I thought, I have to leave. I was already at TU Eindhoven, and then also TNO came along with their spatial ALD activities. And there, I've been there for, what was it? Something like 12 years. There, I have had great times in developing spatial ALD, considered as an option to sort of more commercialize, bring down the cost and that sort of thing, and commercialize to large area. Now the scale up is not scale down in dimensions, but scale up in substrate. So substrates for solar and for displays, and that was a very, let's say, interesting time as well, bringing or pre-marketing, pre-developing ALD equipment for the solar industry. And we were relatively, not smashing, but relatively successful in bringing systems, licensing systems on the market for solar. But as you know, solar has completely left Europe.
Yeah, solar is crazy for ALD right now. I was just in Dresden, and Wayman was from Lead Micro was talking about their systems for Exos. That's wild.
Yeah, they even have they claim something like 8 to 10,000 wafers per hour throughput. It's a massive system, and the system that we developed at TNO was a roll-to-roll system, for example, but also a sheet-to-sheet, and now it is Spark Nano, led by Paul Poot here at the high-tech campus. and they're now focusing more on display and battery application. Solar is out of the question.
So did this transition to working with ALD, did that feel kind of natural to go to it?
Yeah, because back in the early 2000s, when we at Philips did not have ALD equipment, there was equipment at IMEC to which Philips had moved. But the even better development that I started on ALD was in 2004 or so with a Korean company, Yusung Engineering. And believe me, they knew and they know what they're doing. They don't communicate that much because they have that internal sort of pro-Samsung, what is it, cooperation or so. But I remember the first batch, just demo batch that we sent out for them to fill trench capacitors with alumina as a dielectric and titanium nitride as the conductor, the metal, so to say. The very first batch was almost on spec, and as we sort of expected. The second batch was right on spot. We also did, that was 2004. And in those same years, we also cooperated within IMEC with ASM, was also okay. I have to admit that that Yusung was, slightly earlier and but somewhat faster. And the interesting thing was, with ASM, it was the classical conventional ALD that we used to fill up those trenches. With Yusung, it was in fact what is now spatial ALD, because it was a sort of windmill construction, very so with inlets and outlets. And I'll make a drawing. Here you are.
Mm-hmm.
An inlet, an out precursor, co-reactant, and this was nitrogen.
Mm-hmm, mm-hmm.
And the wafer was rotated underneath at a certain, let's say, minor distance. And in fact, for some reason, they even had a sort of a fifth arm on that windmill. Anyway, that reactor was already commercial. It was the Eureka reactor, okay, which was and maybe still is there. How did I come to Yusung? Well, because Philips in Crolles in France, near Grenoble, with this alliance with Motorola and what have you. So Philips Crolles had already such a machine in as early as 2004. We did great things because, in fact, with Yusung we worked out a multiple MIM structure with several of these alumina tinitride lasers repeated, and then we had a world record of almost half a micrometer per square millimeter, which we had already predicted in the roadmap that we could do that. So great work with a spatial ALD. I know that 2008 is sort of considered as the tipping point or the rebirth, the revisiting spatial ALD. Mm. But this work that we did in 2004, we kept it unpublished until that same year, 2008. So we are also in that famous sort of assembly of institutes that reinvented spatial ALD. It's Eastman Kodak, David Levy. It is TNO. But what people do not always know is that in that same year we had the machine was already there. It was Yusung. And we used it to make world record density trench capacitors. And that is a sort of forgotten
It's another instance of a great idea coming a little bit too early.
Yeah. And still a milestone in that same year or even before, because as I said, we started doing this 2004, but kept it sort of unpublished and secret for good reasons, because there were patents, of course, being filed on that. But this is another thing I'm proud of. Yeah, that world record academically, and the Medtronic sort of pacemakers that really make it in the market.
That's really wonderful. And I have to say now, talking about things that you must be proud of, I want to extend a congratulations against you. You'll be receiving I have it here, the Gordon E. Moore Medal for Outstanding Achievement in Solid State Science and Technology from the Electrochemical Society in May. I believe you'll be receiving it. So congratulations for that. I'm sure it must feel incredible.
Well, that feels nice. And of course, it is, I think it, of course, Gordon Moore lived to become a relatively healthy 94 years old person, but I have high regards for him. It's unbelievable as an iconic captain of industry. Every now and then, I have been told that he was appearing himself to deliver in the earlier years this medal award during the ECS spring conferences every 2 years. It is being awarded, and I had hoped. Crazy. He lived or lives in Hawaii. So I had hoped that I could shake hands with the person. Some of my Philips colleagues have done so. I have never had the honor.
That would have been a moment to remember in your life for sure. And yeah, the timestamp, I guess this recording right now, we're only less than a week from when we learned of his passing. So yeah, I think this is even more potent that you're receiving this so soon after.
Yeah, I take it as a double honor. Yeah.
Mm-hmm. What is the thing coming up in ALD that you are really excited to see happen?
Yeah. ALD had the D is I was gonna say deposition. It's not mature as CVD yet, huh? But it is sort of maturing, and you see it coming in more than just the high K metal gate stack or so. Huh? As a matter of fact, what people may know, but not all of them, I guess. But ALD is the main use of ALD is in this spacer-aligned double or multiple patterning. Huh? Well, I'm not going to dwell on that, but that is a process. Call it the poor man's lithography, or so. The poor man's doubling or quadrupling the pitch, the half pitch or so. Why may people not know it? Because it doesn't end up as a layer in the final product. It's only used as a means to refine the pattern pitch. But more and more of these things applications are coming on, and I foresee a lot of other fields, not only in semicon but also in other fields, medical, MEMS, biology or bio nano sort of stuff, and of course it may now just be a sort of curiosity technology or niche at very best, but it will come sooner or later. But again, not until the knife on people's throats is really piercing. But to mention an example, other example is what I'm doing now at University of Twente. It is using ALD. We're studying it. There's nothing on the market yet. Studying ALD as a means to tune and to modify membranes, nanofiltration membranes, becoming very important in the green future technologies. Because those ultrafiltration or nanofiltration membranes, they are now still a bit too wide in pore size and that sort of thing, or they are not yet functionalized enough to keep polar polar liquids out of non-polar liquids for water purification and what have you, or for gas separation in the chemical and petrochemical plants. So that could be an interesting field as well. Another field, I'm working also for a small startup called Carbion, working on CO2 capture, direct air capture. That is normally done by, there's now already quite a few companies out there. Carbion is just a startup. There are already bigger ones like Climeworks, Switzerland, Iceland. They use carbon, active carbon, so that is highly porous carbon, which can be modified with, well, let's say very thin layers on top. Not per se ALD layers, but could be ALD layers also. Those layers, they functionalize the carbon better towards higher CO2 absorption.
Very enlightening. Thank you so much for all of your stories and all of your insights. I want to wrap up with just one final question here. And it's, you've been in the industry and deposition and semiconductor industry for many, many decades now. You're receiving this award, and I mean, you've seen so much happen over your career. And I just want to ask, do you feel there's some life lessons that you've learned in working in this industry and seeing how it's progressed so rapidly and so prolifically over the past few decades?
Yeah. Well, some of my students may or colleagues may now recall what I always told them. I have learned, sometimes in a bad, sometimes in a very good sort of context, a couple of lessons, or call it sort of rules of life. And the number one is, you're never an exception. So yes, I may be awarded, but I'm not an exception. There's so many people having even bigger awards. So that is, well, that's not negative or positive, that's neutral, but you're never an exception. Also meaning, I mean that also, I have been very lucky time-wise. So as I said, in research quite a few times, nothing comes out. But this came out. This came out to be one or two commercial running products. But you're never alone. You're dependent on others, on other people. Yeah, other times, other people. And I have been very lucky with, working with many inspiring colleagues and students, also students, until the day of today. And so, and what else can I say? Another thing, it's a Dutch expression, which translates into, the soup is never eaten that hot as it is served. Meaning that whatever problems you have in a project or with people or whatever, it may seem hot, but you don't eat it that hot. And then comes my other rule: time is your friend, not your enemy. Time is your friend. And the older I get, the more I think that is the case. I've just been lucky. And, Semicon is, I love my wife and my kids, grandkids, but I also sort of love Semicon and the other related challenging topics that I'm doing now. Yeah, I think that's it.
That's wonderful. Thank you so much for sharing. Well, Fred, I think that we can wrap it up here then. Again, thank you so much for coming on to the show and having this conversation with me. This was really, really awesome. And I hope that everybody who is listening has enjoyed your insights and your stories and everything you've had to say about the semicon industry, because I know I have. So congratulations again for the award from the ECS, the Gordon E. Moore Medal. And I hope that I'll be able to see you sometime this year at some conference. I know we'll have many opportunities, I'm sure, to connect. So
certainly at the ECS conference in Gothenburg, we're 8 to 12.
That's right. That's right.
Advertisement. Yeah.
Perfect. Yes, we'll plug it. Maybe I'll have to bring in a photo of Gothenburg into the video here.
Fine.
Well, fantastic. Fred, again, thanks so much. This was really wonderful. I'm really happy to have you on the show.
It was my big pleasure and honor to be in your series. Thank you very much, Tyler. And goodbye to everyone.
Thanks for listening to ALD Stories with Benek. To stay updated on new episodes each month, please follow us on Spotify, Apple Podcasts, or Google Podcasts. We hope you enjoyed the show. I hope to see you again in the next one.